Okay, so this is a final exam review, and I want to start here with number 1, in which we're supposed to do the following computations by hand. So in part A, what we want to do is find the prime factorization of 220. And so the way that we do this in part A is we take 220 and we're going to make the factorization tree here. And so obviously 2 goes into 220 110 times. And 110 is 2 times 55. And then 55 is 5 times 11. And 2, 2, 5, and 11 are primes. And so we see that 220 is equal to 2 times 2, so 2 squared, times a 5, right, times 11, right? So 2 times 2 times 5 times 11. And then in part B, what we want to do is do the prime factorization tree for 66, and that'll give us its prime factorization. So this is 2 times 33, and then 33, obviously 3 goes into it, so this is 3 times 11. So 66 is equal to 2 times 3 times 11. So 2 times 3 times 11. And then in part C, we want to find the GCD, right, the greatest common divisor of 220 and 66. And then we want to find the LCM, the least common multiple of 220 and 66. So to find the GCD, we take the GCD of 220 and 66. And what this is equal to is what they have in common. So I come over here and I say, okay, they have a 2 in common, right? But they don't have another 2 in common. And then they don't have a 5 in common, but they do have an 11 in common. All right, so what do they have in common? A 2 times 11, which is equal to 22. All right, so 22 is the greatest common divisor, right? 22 is a divisor of both 220 and 66, and it's also the largest, right? It's the greatest. And then for the LCM of 220 and 66, this is equal to now, all right, so the most obvious common multiple will be 220 times 66, but it may not be the least. To make it the least, we have to divide out by what they have in common, which is the 22 we found above. And so this is actually equal to, well, 220 divided by 22 is just 10. Right, so 10 times 66, which is equal to 660. All right, let's move on to the next problem. On number 2, it says, let the population P of a city be a function of the number of years T since 1980. Use the formula to answer the following problems below. Round your answers to the nearest person. Okay, so this represents the population of the city after a certain number of years, T years, since 1980. And it says, what was the population of the city in 1980? So remember, in 1980, T is equal to 0. And so in part A, what it's saying is please find P of 0, which is equal to 150,000, all divided by 1 plus 25 e to the minus 0.375, right, times 0. And so to do this, I'll take out my calculator. And so here's my calculator. And I'm going to plug it in, right, to my calculator. So here, second quit. All right, so clear that out. So I have 150,000, so 150,000, divided by, and remember, you have to put parentheses in the bottom because this is all in the bottom, so I'll have to put parentheses around that whole thing. And then I have 1 plus 25 second ln to the negative 0.375 times 0, in parentheses for the exponential, in parentheses for the denominator, and I hit enter, and out pops my answer. So on this one, what do I get? I get, oh, well, there's a mistake up here, right? So I'm going to fix this. For some reason, I had a 2 there. Maybe I hit the 2. I meant to hit 0. Right? Oh, there it is. Okay. So different answer because that 2 should not be there. That should be a 0, right? I have a 0. So this is approximately, if I round to the nearest person, 5,769 people. All right, and then in part B, it says how much did the population change from 1990 to 2005. All right, so the first thing I'm going to do is find the population in 2005. And 2005, remember, corresponds to t equal to what? We start at 80 is 0, so 25. So first I'll find the population in 2005, which will equal, and I can just plug this in, so 150,000 divided by 1 plus 25 e to the minus 0.375, and I plug in 25 for t. I want to figure out this number, and so I can do this simply by hitting second enter, right, pull up the last entry and change that 0 there to a 25. Okay. And I'm going to write this whole number out. I don't want to round it because I don't want to round to the very end, basically. So let's say this is equal to 149682.6046. And then I want to find the population in 1990, which corresponds to t equal 10. Right? So I'll do p of 10, right? 10 years after 1980 is 1990. And I get 150,000, all divided by 1 plus 25 e to the minus 0.375 with a 10 here now. And again, I just hit second enter, and since I've already entered it once, I just changed that 25 to a 10. I hit enter, and out pops my answer here, so 94,461.79047. And I'm going to subtract these two answers because I want to find by how much the population changed. So this is the population after 25 years, this is the population after 10 years, and now I subtract the two. So up here I'll just take 149682.6046 minus second answer, hit enter, and I'll round this to the nearest person, so I get 55,221 people. So approximately for my answer. All right, finally in part C it says, in what year will the population reach 125,000 people? All right, so on this one, you have to be a little bit careful. All right, you don't want to plug in for the input now, right? Time is input. You want to plug in for people stuff, which is the output. So what you want to do is take 125,000, and you set it equal to now the population formula, so 150,000 divided by 1 plus 25 e to the minus 0.375. And then you put a t here because you don't know t. You're actually looking for t because it says in what year. All right, so now the idea behind this is you're going to graph the right, graph the left, and intersect. So hit y equals and plug in the formula on the right, so 150,000 divided by, and now remember when you divide this over here, what are you gonna do? Well, let's make this smaller. Okay, so when you divide this, make sure you put parentheses on the left and right. So I have left parenthesis 1 plus, and I have 25, and I have second ln, and then a negative 0.375 with an x in parenthesis, so that's the right. Hit enter, and I have 25,000 for y2. Right. And now I have to make my window. Right. So to make my window, I have to think, well, how many years is it going to take for this population to reach 125,000? Well, I'll start at 0, and maybe I'll put 50 here for 50 years in the future, and let's see what happens. So hit zoom, zoom fit. So zoom fit. And let's see. I get a graph. I went from 0 to 50. And the formula on the right there gave me this graph. And then the bottom, I have this 125,000 line. and I hit intersect to find where they cross. Great. So second, trace, go down to number 5, which is intersect. First curve, just hit enter. Second curve, hit enter. Third for a guess, just hit enter, and I'll jump right to the intersection. And so here it says t is about 4.29 years. Oops. But I had to be careful. Look, that says 25,000. That means I did something wrong, right? That shouldn't say 25. That should say 125. So I must have put this in wrong. So down here, this needs to be 125,000. Right, so go back, and if you put the same thing in I did, make sure you put 125,000 there. And then everything's the same, 0 to 50. Then zoom fit it. Right. And that changes it a little bit. You can keep the same picture, really. But the line goes up there, so maybe I'll change the line to up here and erase this down here. There. Okay, and now do the same thing. You want to hit intersect. So second, trace, go down to intersect. Right, again, first curve, enter, for enter, enter. Right, and then you get at a different time, of course. Now the y value is right. You should have 125,000 here because my output, in a sense, is 125,000. So t is equal to 12.87553 years. And it says in what year. So to figure out in what year, I started in 1980. And so I add these two numbers together. And so I get in 1992 for my answer. Okay, let's take a look at the next problem. All right, so number 3. So on number 3, we're going to do things by hand. It says perform the following operations by hand. So on part A, I'm going to take 5/9 and I want to add 3/4. So remember, when you add fractions, you need to find a common denominator, and it's very easy to find a common denominator. Right? If you have a denominators of 9 and 4, the common one would just be 4 times 9. So if I put a 4 down there, I put a 4 up here. And I'll put a 9 over here, and I can put a 9 up here. And so this will be equal to 4 times 5 is 20. On the bottom, I have 36. Plus 3 times 9 is 27. On the bottom, again, I have 36. So now they have a common denominator, so I add the numerators together, and I get 47. And I keep the same denominator. So 20 over 36 plus 27 over 36 is 47 over 36. In part B, right, what I have, and there shouldn't be, I don't know why this is there. That shouldn't be there. There's nothing, that doesn't mean anything. All right, so I have 3 divided by 2/5 minus 3/7. And now this involves a little bit of order of operations. So remember, you always do the parentheses first. So this is actually 3 divided by, and I have to get a common denominator. So I put 2 times 7 divided by 5 times 7. Minus, again, 5 times 3 divided by 5 times 7. And so this is equal to 3 divided by, and I have 14 on top and 35 on the bottom, minus 15 divided by 35, which equals 3 divided by 14 minus 15 is a minus 1 over 35. And when you divide by a fraction, it's the same as multiplying it by its reciprocal. So this is 3 times 35 divided by minus 1, which is equal to, again, you say 3 times 35 is equal to what? Well, let's see, 3 times 35. 35 plus 35 is 70, plus 35 is 105. And so this is actually 105 divided by minus 1, which you could just write as minus 105 if you like. Right, so that's the answer for part B. And then on part C, we have to do this multiplication with these complex numbers. So 3 minus I times 2 plus 3i. And now remember, when you're multiplying complex numbers, you have to remember I is actually equal to the square root of minus 1, which tells us if we square both sides, I squared is equal to negative 1. And so now when we multiply, we take 3 times 2, and then add 3 times 3i, so this is equal to 3 times 2 is 6, and then 3 times the 3i is plus 9i, and then we do the next term, right? Minus I times 2 and minus I times 3i, so you get minus 2i, right? Minus I times 2 is minus 2i, and minus I times a positive 3i is minus a 3i squared. All right, so the multiplication is done, the rest is just a simplification, and so now I have 6. You combine like terms, so I have 9i minus 2i, which is plus a 7i, and then minus 3, and then remember I squared is actually negative 1. And you keep going, so this is 6 plus 7i, minus and minus is a plus, and then so it's plus 3, and so 6 plus 3 is 9, and of course you have plus 7i for your answer. Okay, number 4. All right, so on number 4, it says let the amount in an investment A in dollars be a function of the T years since its opening in January 1st, 2000. Use the table below to answer the following problems. Okay, so what happens here is when you open the account, you have $33,000. After 2 years, you have $46,000, and so on. First, we want to plot the data. Okay, so we have to review how do we plot data. And so on your calculator, we can use our calculator here. So take it out. And to plot this data, you're going to want to go to Stat, and you hit Enter, and it pulls up your lists. And so in list 1, you're going to put the input, which is a time, so 0, 2, 4, 6, right? Hitting Enter after each one to move down. Then hit over and put in your output 33,000, Enter, 46,000, Enter, 63,000, Enter, and 105,000, Enter. And then to get a plot, you're going to hit Y equals, right, clear all this stuff out because you don't want it on, and turn on plot 1, so go up to plot 1, hit Enter, and then go down, you can see it's highlighted. And then go over to Zoom, and remember you don't want Zoom Fit now you want Zoom Stat because you want to zoom in on the stat stuff. And if you hit Zoom Stat, you'll get a nice looking plot. So let's do this. Let's draw the plot here. And so you have 0, 2, 4, 6. Right. And at 0, you were at 33,000. So why don't we do this in K? So we'll do like, this was, let's do like 33K. And then at 2, you're at 63,000. So you're up here. Right, a little bit higher, 63K. All right, and then you go up a little higher even more, so right about here. I guess we should draw these little boxes, huh? And then we go up even higher up here. All right, and so this one is at, ooh, I made a mistake here, right? So let's fix that. Right, that wasn't 63, that was actually 46. So over here, we'll write down that this is about 46K, and then a little above it we have 63K. Right, so this was 46K. And then up here we have 105K. Right, so you should label your axes. Right, this is a time, time. Right, T in years. And then this over here is the amount. All right, A. We can write in dollars. And up here we could write this to be, you know, my investment. Let's give it a title. Investment amount. All right, so is that it? Let's think. So plot the data. Does it look like that? I mean, it's good enough. You know, I can, looks, you know, I might actually move one of these little points down a little bit further, right, just to make it look a little bit better, more like the picture, because it looks like this one is actually a little down a little bit further. And I might even clean this up a little bit, because over here just doesn't look very good. So maybe I'll clean it up a little bit. So this one was my 46K. That's better. Okay, there's my title. All right, and then in part B, it says what? It says use exponential regression to find an exponential function that will model a as a function of t. Round your regression parameters to 2 decimal places. So in part B, let's do that right here. I can take my calculator and let's move it over here a little bit. Oops, I don't want to do that. Okay, and I want to find, seriously. All right, so I want to find exponential regression, and so I'll do that, hit stat, go over to calculate, and then you can scroll through these and you'll find one that says expreg, which stands for exponential regression. You hit enter, and out pops your answer. And I'll round these to 2 decimal places. So let's just move this over. So this is going to be equal to, A is equal to, and I have 31,897.68, right, times, it says, you know, times here, so A times B, so that's times 1 point, the 2 decimal places, so 2, 1, and that's raised to the t. And I can even plot this on my plot. I can graph it on my plot if I want to, just so you can see how nicely it fits. The question doesn't ask this, but you can do it. So 31,897.68 times 1.21 raised to the x. And just hit the graph button, you can see how it kind of approximates those points. Right? So that's the whole point of this problem, right? To find a curve that gives you a good approximation to your data. All right, then in part C it says use the exponential model to estimate the initial value of the investment in 2000. All right, so the idea behind this question is that these numbers actually represent things. And this number right here, right, this number that I'm circling in blue, that's the initial investment. Right? So the answer for this one would be $31,000. $31,897.68. For part D, it says use the exponential model to estimate the yearly percentage rate growth. Right? So this should say to estimate, right, the yearly percentage percentage rate of growth. And so the idea behind that is that you look here at this number, and that's the growth factor. To get the yearly percentage rate of growth, what you need to do is rip off the 1, and you're left with 0.21, which is 21%. Right? So the percentage rate of growth is just 21%. Okay, so let's see. Part E, what do we need to do in it? It says use the exponential model to estimate how much money will be in the account in 2015. So now remember 2015, right? T starts in 2000, so T is equal to 15 here. And this is not output stuff, this is input stuff, so you want to plug this in for T. So in part E, you want to find A of 15, which is equal to 31,897.68 times 1.21 to the 15. Right. Now you have two choices. You can use the graph to do this, or you could just use the clear screen. I'm just going to use a clear screen, I think, and practice plugging this in. So I do 31897.68 times 1.21 raised to the what? Raised to the 15. Hit enter, and out pops my answer. And so to 2 decimal places, this is $556,595.45. Right, so after 15 years, I'll have over $500,000 in that account if it keeps on growing like it has been. And then finally, on part F, right, it says use the exponential model to estimate the number of years it will take for the account to grow from 75,000 to 125,000. All right, so $75,000 and $125,000. It's not input stuff; it's output stuff. So you're going to set it equal. So let's do a $125,000 first. So you'll take $125,000. That's output stuff. So you set it equal to then 31897.68, 1.21 to the t. And then I'll also take $75,000 and plug that in for A. That's the output. So I set it equal to 31,897.68, all times 1.21 to the t. And I need to solve these for t. And so the way I'm going to do this is I'm going to graph the right, graph the left, and intersect. So on my calculator, hit y equals. Right? Everything's, the formula on the right's all set up. Right? I have it right here, 31,897.68 times 1.21 to the t, right, to the x. So over here, I'm going to put 75,000 in for y2. And then I'm going to put 125,000. Actually, maybe I'll put 125,000 in first since it's on top. So I put 125,000 first. It doesn't matter though. And then 75,000 in for y3. And then I'll hit zoom fit. Let's look at my window actually first. Right, let's go to graph so you can see what happens. So if you just hit graph, you see one, and that's it. Okay, so you didn't see two lines, right? The reason you didn't see two lines is because your window's kind of small. So what I would do maybe is set this at 0, and then maybe I'll go to 10 years, right? From 0 to 10 years. That's just a guess, and see what happens. So I'll go zoom fit. And I'm looking for two lines to go across. The lines are to 75,000 and 125,000. So first it graphs my formula. And there's one line, that's 125,000, and there's a 75,000. So I had to go up a little bit to see both lines. And so now I'm going to hit second trace, and I'm going to go to intersect, which is number 5. And first curve, great. Second curve, the 125,000, great. Hit enter again, and it's just spit out an answer for me. And I'd probably, down here, I'd probably draw the picture, so the picture's credit in case I did something wrong. All right, so I went from 0 to 10. Right, and I got these two lines here. And I do intersect basically. I'm going to do this twice. All right, so on one I found, for the 125,000, I found t to be equal to 7.1649244. And now I'm going to do the other intersection. So I hit second trace, go down to number 5. First curve, yes, but be careful now. After you hit enter, it says second curve, and it puts you back on 125,000. I don't want to be on 125,000. I actually want to be on 75,000. So if you just hit down, it's going to scroll down basically, or jump down to the next curve, which is 75,000. Now I hit enter. Yep, that's my second curve. Give it a guess. Just hit enter again, and it'll spit out how long it takes for the count to reach 75,000, which is 4.4851181. And I take these two times and I subtract them, and that'll tell me how long it will take for my money to grow from 75,000 to 125,000. So I'll just hit second quit, clear this out, and plug in these times. So I have 7.1649244 minus 4.485, and I think that's 1181. All right, 1181. Hit enter, and out pops my answer. In this one, I'll round just to one decimal place. So it's approximately 2.7 years. So it takes about 2.7 years for my money to grow from $75,000 to $125,000. And I think that ends that question. All right, the next one. Right, number 5 is asking if these events are mutually exclusive or non-mutually exclusive. Remember, the idea of mutually exclusive when you draw the two events, if I have event A and event B and there's no overlap, these are then mutually exclusive. Non-mutually exclusive events, when you draw them, there's always something in their overlap. So it looks like this MasterCard symbol here, so A and B. And you have something in here, whatever it is, something, maybe it's a number, whatever. There's something in there. All right, so on part A, it says roll a die. All right, so what does that mean? Right, you roll a die 1 through 6, and it says get an odd number or get a triangular number. So now we have to think. Okay, so here is our event A, so we'll call that A. And here we'll call event B a triangular number. And so we can make a little diagram here and say, okay, we have event A, which is an odd number, and we have event B over here, which is a triangular number. So odd numbers are easy to write down. Right? For a die, you have 1, 3, and 5. And then for triangular numbers, we have to remember the definition of a triangular number. The idea is you can represent it as a triangle. So 1 is actually a triangular number, and then so is the next one would be 1, 2, 3. So it's 3. And then after that, let's see what else we have. 1, 2, 3, 4, 5, 6. And then 6. And of course, that's it because you can only roll 1 through 6. So in A, we have 1, but that's also in B, so that's in the intersection. So is 3, right? So 3 is in there too. 5's in A, but not in B, so 5's over here, and 6 is in B, not over here. That means outside you have, let's see, 1, 2 is outside, there's 3, and 4 is outside. Now you have them all. All right, so we can look back up here and say mutually exclusive or non-mutually exclusive. Obviously, it's non-mutually exclusive. Because you have something in the overlap. You have a 1 and 3. These are both 1 and 3 are odd numbers and they're triangular numbers, so A and B are not, the two events are not separate. In part B, it says select a student in your school. The student was born in May, A, and the student was born in winter. Right, so if you think about this, right, and you think about all the students that were born in May, and so you can draw a picture if you like. So here we can draw a picture. So A will be all the students that were born in May, and then B will be all the students born in winter. So here they are over here. These are all the students born in May. Let's just put May underneath it, so it's real obvious. And then winter, well, May is not in winter, right? So over here are all the students born in winter, right? However you want to define the winter months, it's certainly May is not in a winter month. Right? So it's obvious that these are mutually exclusive. And that's it. So that answers question number 5. All right, so on number 6, what we have are these ancient numeral systems. And so on the first one here, we're going to need a little help right from our sheet. And so if you pull out the sheet that I gave you, you can look over here at the Egyptian numeral system on the right, and you just basically write down the numbers that these symbols represent. So an astonished man here is 1,000,000, so I'll write 1,000,000 underneath it. And then a lotus flower says it's 1,000, so I'll write 1,000 underneath that. There's 2 of them, so there's 1,000. And then a scroll here is 100. And then I have 3 vertical staffs, which is 3. And so if you add these all together, what you're going to get is 1,000,000. And then you have 2,000. And then 100 and 3. And so that's what these Egyptian numerals, this is the number of things these Egyptian numerals represent. And the next one, number 2, let's do it down here so we can have a little space. So a number 2, what do we have? I have this number, and it's written base 6. So I have 5, 2, 4, 3, base 6. And if you understand what this base 6 means, this means that this is the 1 spot. And in base 10, this would be the 10 spot. But since it's base 6, it's the 6 spot. And now in base 10, this would be the 100 spot, the 10 squared spot. But in base 6, it's 6 squared, which is 36. And then here, in the 5 is a 6 cubed spot, which I'd have to look up, right? So 6 cubed, whatever that is. So this is actually represents 5 6 cubes, 2 6 squareds, 4 6s, and 3 1s. So what this is actually equal to, is 5 times 6 cubed plus 2 times 6 squared plus 4 times 6 plus 3 times 1. And I can do this on my calculator. So my calculator what I'll do is just, I'll just take 5 times 6 raised to the 3 plus 2 times 6 raised to the 2 plus 4 times 6 plus 3 times 1 if you like. And I get out 1,179. So this is equal to 1,179. Okay, and part 3, maybe I'll just do part 3 right underneath it. All right, so for part 3, again, I need my table. All right, I need my table for the Greek numeral system. All right, so here's the Greek numeral system on the right. And what I need to do is translate these numerals into the number of things they represent. So like this E looking like thing, this is the epsilon, and it represents 5 things, so I'll put a 5 there. This thing, I look through this chart, should be in the 10 spot. So in the 10 spot, what do we have? Oh, it's a lambda, and so that's 30 things. That's 30. And then this W thing, it should be somewhere over in the 100 spots, and so that's omega, which is 800. And here you simply add these together and you get 835 for part 3. Part 4 I'm going to do down here. So on part 4, what do I have? I have 2 triangular wedges, a nice big space with a vertical staff, and then another triangular wedge, nice big space and triangular wedge, and a bunch of vertical staffs here. And I'll pull back up and I'll look at the Babylonian numeral system because I can recognize these symbols over here. So 2 triangular wedges is a 20. So this actually represents 20 things, right? For that's first spot. And now 1 vertical staff is 1 thing, and then a triangular wedge with 5 vertical staffs. We come over here and you see, oh, that's 15 things. But you have to be careful. You can't just add these things up, right? Because the Babylonians used a base 60 numeral system, and so what you really need to do is write down the number of things this really represents. So this is actually 15 ones. That's great. And now here, if this was our numeral system, this would be 110, but since it's the Babylonian, this is actually 160. And over here, this is not 20 hundreds, right? This is actually 20 60 squared. No, don't be confused by what I wrote here. These are not fractions, right? I'm just writing the position. Right, so this is the 1's position, the 60's position, and the 60 squared position. So what this is equal to, you have actually 20 of these 60 squareds. So 20 times 60 squared. Plus you have 1 times 60, right? So 160, so 1 times 60. Plus you have 15 ones, so 15 times 1. And so I can use my calculator and it'll tell me I have 20 times 60 raised to the 2. Plus I have 1 times 60 plus 15. I can put times 1 if you really want to. And so I get out this Egyptian numeral actually represents 72,075 things. This really isn't as foreign as you think. You know, if you think this is actually represents the number of seconds here. Like if you have 20 hours, 1 minute, and 15 seconds, and you convert it to seconds, the way you do that, you have 15 seconds, right? 1 minute is actually 60 seconds, right? So you have 60 seconds there. And 20 hours, well, to convert that to seconds, you multiply it by 60 squared because there's 3,600 seconds in an hour. So this is how many seconds are in 20 hours, really. And so basically, you could actually think of this as 72,075 seconds. All right, the last one we can do right underneath it. This is the Roman numeral system. Again, we can pull down and look at it. So here's the chart for the Roman numeral system. And we know that M here is 1,000. C is 100, and D is 500, so you have to be a little bit careful here. You probably do not want to write 100 and then 500. The thing is here that C is before the D and C is less than D. So if you have 100 and then you have 500 afterwards, this is actually 400. Right? We see this most normally when we write like an I and a V, and that's equal to 4. Right? So in the Roman numeral system, if you write a letter and it's less than the next one, you subtract. You don't add. And now X is 10. V is 5, and 2 i's is 2, and you simply add these together to get 1,500 400, and then 17. Right, 10 plus 5 plus 2. Okay, then on number 7, right, what happens here? Okay, so now we hit a probability question. So a penny is tossed 3 times. Use a tree diagram to answer the following questions. How many possible outcomes are there? How many include at least 2 heads? How many include exactly 1 head? So the idea of a tree diagram is you say, okay, I can throw a heads or I can throw a tails. That's the first time. Then the second time I could throw a heads or a tails. Right, so I could throw a heads or a tails. And the third time, I'm just doing this 3 times, like penny is tossed 3 times. I could get a heads, tails, heads, tails, heads, tails, and finally heads, tails. And what this allows me to do is to write down all the possible outcomes by following the branches of the trees. So it's like H, H, H. So H, H, H. Or I could go H, H, T. H, H, T. Or H, T, H. H, T, H. Or H, T, T. H, T, T. And do the same one for this next branch down here. So I have T, H, H. T, H, T. TTH, and then TTT. All right, so for part A, it should be pretty easy to answer. You count these up. So how many possible outcomes do you have? There are 8 outcomes. And then for part B, it says how many of these include at least 2 heads. All right, so what I'm going to do is change to blue here, and I'm going to circle the one that have at least 2 heads. So this has 3 heads, so that's okay. At least 2 means 2 or more. And this has 2, right? This has 2. Right? Don't circle this one because this has just 1 head, so it doesn't meet the criteria at least 2. This has 2 heads. This has 1 head, and no head. And so this answer is 4. Right? There are 4 that have at least 2 heads. And then part C, let's do a different color. Let's do green. Right, for part C, it says how many include exactly 1 tail. Okay, so this has no tail, so I don't do anything of that. This has 1 tail. This has 1 tail. Right, this has 2 tails. This has 1 tail. 2 tails, 2 tails, 2 tails. And so I see there are 3 that have exactly 1 tail. Okay, let's take a look at the next problem, which is number 8, which is basically calculator arithmetic. So it says use your calculator to determine the numerical values of the following problems. You should round your answer to 2 decimal places. So take out your calculator, and let's move this over here, and clear this out, and clear that out. And we want to enter the first expression. Now let me remind you, to put this into your calculator, you're going to have to put parentheses on top and on bottom. So I'm going to do left parenthesis 7 plus second square root 3, in parenthesis for the square root, and then in parenthesis for this parenthesis in red. So that's the top, and then divided by left parenthesis 2 second square root of 5, in parenthesis for the square root, in parenthesis for the bottom, hit enter, and out pops my answer. So this one is approximately 1.95 if I round to 2 decimal places. All right, let's do part B now. So part B, you're going to have to put parentheses not on the top, because in the top you just have one number, 100. But you're going to have to put it in the bottom because you're doing a calculation down here. You want to subtract. And it's obviously all in the bottom. All right, so you take 100 and divide by left parenthesis 5 minus 1.3 second ln to pull up the e to the button, negative, so remember you hit this negative sign next to the decimal sign, you can't hit the minus sign, so negative 0.023. End parenthesis, right? First parenthesis here is for the exponential, that's for the denominator. Then hit enter again, and out pops my answer. This one's approximately 26.81. And now the tough one is this last one here, so let's move it over and let's do it. And so on here, let's just clear everything out so that we start over. Right, so you hit left parenthesis 4 raised to the negative 3, so negative 3, plus second square root of 5, in parenthesis to close off the square root, plus 2, and then hit the pi button, so second raised to gets to the pi, in parenthesis, second square root, second ln to pull up the e to the button, you put a 2 in there, in parenthesis for the exponential, plus second square root, and then put 12.7. Oops, for some reason the 2 7s popped up, but hit in parenthesis, right? So just after 12.7, hit in parenthesis, divided by 8.9, in parenthesis, hit enter, and out pops your answer. Right? So this one is approximately 23.82. So approximately 23.82. Okay. Number 9. All right, so in number 9, what we want to do here, we want to write 87 in the following numeral systems. So write it at base 5 numeral system, and then in the base 2 numeral system. So let's do part A first. All right, so on part A, what do we have? We have 87. And to write it in base 5, the idea is you have base 5 cups. So you have a 1's cup, a 5's cup, a 5 squared cup, which is 25. So it's 5 squared. And then a 5 cube cup you don't need because 5 cubes 125 and 87 is smaller than 125. So then you ask yourself, well, how many markers do you put in the 5 squared cup to get as close to 87 as you possibly can? And that's 3, because that doesn't represent 3 things, right? That represents 3 times 25 things, so it's 75. And then how many things left do you have to represent? Well, from 75 to 87, that's what, 12 things? And so let your brain go, and it says, oh, 2 things there, that's 2 5s. And you have 2 1s. Right, so 3 gets you to 75, 2 gets you to 85 there, and then 2 1s gets you to 87. So this is equal to 322, and you write a little base 5 down here, right, at the base, right, to indicate that this is all base 5 stuff, not base 10 stuff like we normally use. And then for part B, to write it in the base 2 numeral system, right, again, you go way out over here, so you have a 1s, a 2s, right, a 2 squared, which is 4, a 2 cubed, which is equal to 8, a 2 to the 4th, which is equal to 16, a 2 to the 5th, which is equal to 32, and then a 2 to the 6th, which is equal to 64, right? And then 2 to the 7th is 128, and that, of course, is too big. Right? So you start here, and you say, well, how many times does 64 go into 87? You say, oh, just once. Right? So that 1 represents 64 things. And then if your math's a little rusty, what we can do here is you can say, okay, well, how many things do I have left? Well, you can count up to 87, or you can just say, oh, 87 minus 64. Right? If you want to avoid the arithmetic, oh, I have 23 things left. And you could do that in your head if you really wanted to, right? And so 23 things left. So how many things do we have in the 32 spot? Well, 0, obviously, because we have 23, right? And because you can't, 32 doesn't go into 23. Now, 16, oh, there's 1 thing, right? So if you take away 16 from 23, how many things do you have left? Oh, 7. So can you put anything in the 8 spot? No, because 8's bigger than 7. But then you get to 4, and you say, oh, I can put 1 here. If you take 4 away from 7, you get 3 left. And so I can put a 2 there. Now I have 1 thing left, and I put a 1 there. And so this is 1, 0, 1, 0, 1, 1, 1. Base 2 represents 87 things. And again, you can count this up. You know, this one is 1, 1. You have 1, 2, 1, 4, 1, 16, and 1, 64. If you add those up, you should get 87. Okay. Let's look at the next problem. So in the next problem, it says there are 210 boys and 84 girls at a camp. You would like to divide the kids up into the largest possible all-boy groups and all-girl groups, each of the same size. Find the number of kids in each group and the number of all-boy versus girl groups. So on this one, you might want to draw a picture. Right? So you have 210 boys and 84 girls at camp. Right? So my picture, I might look like this. I have a bunch of boys, so 210 boys. And I have a bunch of girls over here. 84 girls. And you would like to divide them up. So I want to divide them up some way. I don't know how. But I want to divide them up into the largest possible all-boy, girl groups, each of the same size, right? So I want to break them up in groups of each the same size. And I want to find the number in each group and the number of all-boy and all-girl groups. All right, so this problem is an LCM or GCD problem. And since you're dividing them up, you have to understand that your answer in the end is not going to be bigger than 210 or 84. It's actually going to be smaller because you're trying to divide them up. Right? That means you're not looking for the LCM. Right? You're actually looking for the GCD, right? The greatest common divisor of 210 and 84. Right? So this is like my equation. Find this, and I'll basically answer what I need to find. Find the number of kids in each group and find the number of all boy groups versus girl groups. So to solve this, what I need to do is find the GCD. So I'll take 210 and make a little tree for it. So this is 2, all right, and this is 105, right, which is 5 times 21, and 21 is 3 times 7. Right, that's a 3 there. And then I can do 84. Right, 84 is 2 times 42, which is 2 times 21, which is 3 times 7. All right. And now I can find the GCD by circling what they have in common. So they have a 2 in common. They don't have a 5 in common, but they certainly have a 3 in common, and they have a 7 in common. So their GCD is equal to 2 times 3 times 7, which is 6 times 7, which is 42. Right, so what does that tell me? Well, you can look over here and you'd say, okay, well, I can divide up. Let's do 84 first. Let's use a different color. So I could do, 42 and one other, just 42. Right, so there's just 2 groups of girls. And over here I could do 42 and 42. Right, that's 84. And then 42. Right, well, what does that give me? That gets me to 124. Right, and 42 again. And I can keep on going, and again, you can use your calculator to do this. In fact, you can do it relatively quickly by saying, what, 210 divided by 42. You'll see that it goes into it 5 times, so there's one more, 42. And this helps us answer our question. So find the number of kids in each group. So there are 42 kids in each group. And then how many all-boy groups? Well, there's 1, 2, 3, 4, 5 all-boy groups. So 5 all-boy groups. And just 2 all-girl groups. All right, so this is my answer.